Hello. It's an explanation of expectation algebra and using it when combining normally distributed variables. We've already been through in our work earlier, in the earlier videos, and looked at a generalized combination of two variables, that z is ax plus by, and we went through and calculated the expectation of ax plus by and showed that that would be a times the expectation of x plus b times the expectation of y. So if we were working with two normally distributed variables, they will have means x and y, mu x and mu y. Then the mean of population mean of a combined variable will just be a times mu x plus b times mu y. And similarly, if we wanted to look at the variance of this combination, so the variance ax plus by will equal a squared times the variance of x plus b squared times the variance of y. And if we rewrote that as variances in the sigma format that we use for a normal distribution, so the variance of the variable, normally distributed variable z, will equal a squared times the variance of the variable x plus b squared times the variance of the variable y. Now so we effectively start from the position that we know what we're going to do with the mean and variances. What we don't know is, well, what sort of distribution is this going to be? And we can look at that by looking to calculate the PDF of the combined distribution. So if we start off with the x variable, where x is normally distributed with mean mu x and variance sigma squared x, then we know that the PDF of that, the f of x, is going to be 1 over root 2 pi over sigma x times e to the minus x minus mu x over sigma x squared over 2. And we know the same thing, same format for the y, that the fy is going to be the same general form, isn't it? But it's y minus mu y over sigma y squared over 2. So we can look at the combined variable z as being x plus y, and we now can use convolutions here to look for what the PDF of that's going to be. Well, the PDF of that is going to be the if we do this as a distribution of, I'm just going to do it like that, here's my y going up, here's my x going along, and we know that at the boundary line here, then our value of z on this boundary here must equal, this is effectively the line x plus y equals z, where z is the value that we're interested in, because this is our boundary of our probability distribution. And if that's true, then we can see that for any x value, if I take my x value as being here, then my y value has got to be z minus x. So what I'm going to do here is, therefore, we know that our integral that we're interested in, the area over here, all this area, this volume actually, because we're in a space now, is going to be, for each little part here, we've got our fx value, probability of that happening, and then we've got our fy, which is effectively the values up to this point here, because that we know what that point is there. So that's our probability, our PDF for the y, but we've substituted in for y, we've substituted in x z minus x. So what we have to do is evaluate that that integral there. And if we substitute in our two normal distributions, then we're going to end up with our 2 root 2 pi, so they come together to become 2 pi, our sigma x and our sigma y out the front. And then we've got our integral, so we've got our e to the power in relation to our y, which is going to be to have as x minus z in, and then we've got our e to the power with our function x squared over 2. Now what we can do is, if we complete the square, if we bring these two together is a single expression, and then we add them, sum them, and then we complete the square, and we want to complete the square in x, so this is what we get here. And if we do the complete square in x terms and we keep those inside, they have to stay inside the integral. So if we've completed the square, we end up with this here on the integral on the right hand side, which is all the functions of x in. Yeah, but we then get some leftover terms if we do that by completing the square, and those terms are not functions of x, they're only functions of z, and therefore they can come outside the integral. And these are the terms that come outside. It's e to the z minus mu z over sigma z, where we've defined sigma z here. The most important one is sigma z equal, and we're using inside sigma z and the sigma and the mu of z from up the top here. Let's go back and see where we had them. Remember, we had these equations here. So these are our equations for mu z and sigma z. Okay, so what we've got here is that, and we've got sigma z on the bottom. And if you have a look at this whole term here, that is a normal distribution in z. There we go, using those two terms, mu z, sigma z. Now this second part here, the right hand side, this bit here, is an integral that we can resolve, and if we complete the integration and we find that this integral times this multiplier at the front, well, this integral basically is root 2 pi sigma x dash. That's what this will evaluate to, and therefore effectively it cancels out with that one there. Excuse me, like that. Those two are going to cancel out, so this has got a value of 1 equals 1. Yeah, and therefore we find that the PDF of our combined distribution is this PDF here for z, for our combined value, which is a perfect normal distribution. So therefore we've proved that if we combine two normally distributed variables in a form, we get another normally distributed variable. Okay, so that basically brings us to the second part of the summary that I prepared. If we combine two independent normally distributed variables, x and y, we create a new normally distributed variable, z. So this is our combination, and that z will be normally distributed where mu z, the mean of z, is a times plus or minus b of mu y, so the two means, but the sigma z of our sigma z squared, our variance of our z, is going to be a squared times variance of x plus b squared times the variance of y. And that allows us to combine two normally distributed variables, independent ones, a bit like we did in Poisson in S2, that we now know that it's another, what we looked at before, two Poissons combined create another Poisson. Here, two normals combined create another normal. So I hope that's of use.